So this particular one is going to help us find multipliers from a table and from a situation. We're going to look at how multipliers relate to a percent increase and decrease. We're going to look at how to write the equation given a situation, a table, a graph, and then we're going to look at situations that might make sense for a table or a graph. We know that exponential growth or geometric sequences are related to one another. We need to find what is going to multiply over and over and over again, because that is what makes exponential growth. It's multiplication. So once we figure out that it's not, that's not how you spell multiplication, but you guys can stick with me. Once you find out that it's not additive or linear growth, then you can start looking for the multiplier. And you find the multiplier by dividing term 1 by term 0, or term 2 by term 1, or term 3 by term 2. It doesn't matter. It just has to be the one after it by the one before it. So in this case, I could divide 130 divided by 100, and that would give me 1.3. Or if you wanted to write it in the way that you would put it in a calculator, term 2, 169 divided by term 1 of 130, it's going to give 1.3. So that's how you find the multiplier. And just a reminder that this multiplier includes two pieces. It includes the original 100% and the new 30% growth. If we just multiplied by 0.3 or 30% in decimal form, you would just end up with the new 30 people instead of the original 100 plus the 30. So we have to multiply by 1.3 or 1.30 to give us the whole thing. And so the multiplier gives us the whole thing. So what we looked at before, in the table, we have 100% of the people who were affected, and then the next day there would be 30% more. So we would want to find out, how do we find 130% of the original, because it's growing by 30% a day. That would be the 1.3 or the 1.30 we had before. Now if it's dropping by 30% a year, if we only multiplied by 0.3, then we would find out how much it dropped. But we want to know the total left. So then we take 100 minus the 30, which is going to give us 70, and we put that in 70. So the multiplier is going to give us the total. If we just multiplied by the percent, we'd find out either how much more there was or how much less there was, but we want to find the total. So percent growth, an increase, you're going to always have a 1 something in front of it. And with like compound interest, 2% interest would be 1.02. And like a 20% markup would be 1.2. And tax or tip, let's say you wanted to leave a 15% tip, and you wanted to know the total amount you're going to spend, your bill and your tip, then you would multiply by 1.15. If we're talking about a population decline, for example, of 15%, that would be 100 minus 15. So that would be, we would multiply by 0.85, because that would be how much was left after the population had declined. Discount, for example. Discount, by the way, and markup and tax and tip are not really decay or exponential growth, because they're one-time calculations. But if I had a 25% off bill and I multiplied by 0.25, that would tell me how much I'm saving. But if I want to know how much I was spending, I would multiply by 0.75. So that's how the multipliers work. The multipliers give you how much in total. Total left if it's a decay, or total amount if it's an increase. So the original 100% plus the increase. Here with our graph, I decided that the situation was going to be that the population of monkeys was dropping at a certain rate, and I will talk about how I figured out that it was 12.5. So I decided that the situation was the number of years and the number of monkeys, and it starts out in the 0 year at our y-intercept at 16,000, and then the first year was at 14,000. Now you can eyeball the curve, but what we're trying to find out is the multiplier, because this is exponential growth. It's showing that curve going down. So we can use the term 0 and the term 1 and the term 0. So we're going to multiply. Notice it's going down. It's going down. It's going down, which means we're going to expect a multiplier that is less than 1. So we're going to do 14,000 divided by 16,000, and you end up with 0.875. That's our multiplier. And so we would continue using that multiplier to find the remaining years. So I multiplied 0.875 times 14,000, and I got 12,250, and then I multiplied by 0.875 one more time, leaving me with 10,719. I am rounding to the nearest monkey. So whenever you're looking at these situations, you have to make sure you round in a way that makes sense. Because it's a multiplier of 0.875, that means that 87.5% of the population is left each time. That means 100 minus 87.5, that gives me the 12% rate of drop for these monkey populations. The equation always is A times r to the x, or A times r to the n if it was a sequence. In this case, the A is the $16,000 monkeys, not money, monkeys, and then the multiplier of 0.875. And x stands for the number of times we're multiplying that multiplier. In this case, the number of years the monkey population is being looked at. With this one, there are lots of things you could think about, but I thought we could think about money, where 3,000 was my initial investment, and 1.04 means when I calculate by 1.04, it's gonna give me my original 100%, the 3,000, and 4% more each time. So this one deals with money, so we're going to go ahead and I multiplied by 1.04 each time. That means I'm getting money on my money. So the first time I made $120, and the next year I'm making 4% on the original 3,000 and the $120 that I got in interest. So that's why exponential growth, compound interest, is way better than simple interest. Initial investment is your A right here, and your growth factor is 1.04, which shows a 4% growth. By the way, this is a sequence. It's considered a sequence because we only deal with counting numbers as our input. We don't get money halfway through the year, and the money goes into your account at the end of that year. The money goes into your account at the end of that year. So it's a sequence. So in this particular case, 10 founders. That's our A. And it's growing by 20% a year. That means I can find 20% of 10, and that's 2 people. And I can add that to the original 10, and that's my 12 that's right here. Or I can multiply it by 100% plus the 20 over and over and over again, and that's going to give me the total amount. So here's a reasonable sketch of this. Here's 10, and it's moving in an upward facing direction. When I ask for a reasonable sketch, by the way, I mean the y-intercept and the right shape and direction. This particular case, since we're multiplying by 1.2, you're going to end up with here, you end up with 14.4. Here you end up with something like 17.58 or something like that. And this one was 20.78. So I rounded to the nearest person. 14.4, that's going to be 14. Whoops, I wanted the eraser. That'd be 14. 17.5 something, that'd be 17. 20.78, we're rounding to the nearest person. So this is not a sequence, because they could go ahead and they could hire people in January, they could hire someone in June. It's not necessarily at the end of each month. So this one is a function. You can call that y or f of x. With this bouncy ball, we have two things we have to do. The situation is a ball is bounced, but we don't yet know how quickly or what percent of the height is dropped each time, so we have to find that information. So we're going to find that multiplier. The multiplier multiplies forward this way, but we don't know what it is, so we can find that by dividing backwards. So I'm going to take term 3 and divide it by term 2. So 67.6 divided by 84.5. And that's going to give me a multiplier of 0.8. So it's multiplying by 0.8, which means that's 80% is left. And that means we have 100 minus 80 was 20% drop each time. It drops 20% of its height each time. Now the only thing we need left is to find our zero term, because we need our zero term to figure out the rest of the situation. What was it dropped by? How high was it dropped by? And then we need that also for our equation. So I'm going to go ahead and erase this piece so I have some space. It's not letting, okay, there we go. So because we multiply by 0.8 going forward, we can divide by 0.8 going backwards to find our missing pieces. So 84.5 divided by 0.8 gives you 105.6, and I'm rounding to the nearest tenth of a centimeter because that's what was done before. And then when I divide by 0.8 again, I get 132. So the ball is bounced, it drops 20% each time, and it started at 132. So that gives us the opportunity to write the equation. All we need, and this is a sequence, because you can't talk about a half of a bounce. So T of n equals the original 132 as a multiplier of 0.8, which signifies a 20% drop for every bounce.